So recall that where we stopped is here. Group homomorphism phi from G to H is a function. Phi such that phi of G1, G2 is phi of G1, phi of G2. So this product here, before we apply the function, the product is taken inside G. After we apply the function to the individual G1 and G2, the product is taken inside H. So this is what we mean by group homomorphism. And we observed a few things. Phi of the identity element of G is the identity element of H. To phi of G inverse is phi of G inverse. So this, before we apply the function, the inverse is inside G. After we apply the function, inverse is inside H. So these are two things. And then we talked about 3. The image of the function, image of phi, is a subgroup of H. And for the kernel of phi, that is the set of G inside G, such that phi of G is the identity element of H, is a subgroup of G. And we also observed that phi is injective if and only if kernel of phi has to contain the identity element of G. It is exactly that. So this is where we stopped before the exam. So now, so we want to see a few more properties about homomorphisms. Then I will discuss just a little bit about symmetric groups today, okay, permutation groups today. And then beginning with the next lecture, we will discuss an important notion called groups acting on sets, okay, or otherwise sometimes called group actions. Okay. So we will start thinking about it, you know, in small examples now itself, because that's sort of an important concept. And many of the things that we study about groups can be simplified, or at least it can be visualized in a simpler way once we understand this idea of groups acting on sets. So that will be the next lecture. So today the plan is to just cover more about homomorphisms, and then just basic things about permutation groups, symmetric groups, SN, which is an important example of finite groups. So that's the plan. Definition. Let H be a subgroup of G. Left coset of H is a subset of G of the form A times H. This is an abbreviation for AH, where H is inside H and A is inside G. So take an element of G, A, and then look at product of A with an element of H, A first and then element of H next, and do this for all elements of H. That is called a left coset of H. Yeah, left coset of H. It's understood that it is taken inside G. So this is so this is also the notation, and it is called. I mean, the left refers to the fact that elements of G multiply H on the left side. That's all. Okay. Similarly, a right coset of H is a subset of G of the form H times A. This again, by definition, H A, H is inside H, where A is in. Okay, so why do we look at this? So let's make a quick observation about cosets. Lemma. Let A and B be inside G and H be a subgroup of G. Then A, exactly one of the following situations hold. So they are mutually exclusive. So let me put in parenthesis mutually exclusive, but it's clear from the way that exactly. Okay. 1. AH is equal to BH. That means the two cosets are the same. Okay, so these are subsets of, okay, maybe I'll add again explanation in brackets. Okay. These are subsets of G, okay, and they are equal. I mean, maybe I should just write one sentence. That is, these two subsets of G, these two are the same. There are two subsets of G, they are the same subset. That's the first assertion. 2, AH is disjoint from BH. There are only two situations. They can't have a non-trivial intersection unless they are the same. So this is an important, I mean, this is a property about cosets that come in handy. We'll use these things later. Okay? But so proof. So we are asserting that exactly one. Okay, first of all, it is clear that these are. Yeah. So first of all, it is clear that these are mutually exclusive because if I mean if it's non-empty, I mean the intersection is either empty or non-empty. Okay, then it is saying that if it's non-empty, then it is the two sets are the same. Okay, so these are mutually exclusive is clear. Okay, so what one needs to show is that if the intersection is not empty, then they are the same sets. That's what we need to show. Okay, so we need to show that. So that's, I mean, so convince yourself that this is what, I mean, convince yourself reading this later that if AH intersect BH is not empty, then AH is equal to BH. Okay, we'll write this down in more concrete ways, which is what we will check. Okay, but right now, logically, just convince yourself that this is what we need to do. If it is not empty, then the two sets are the same. If the intersection of the two subsets is not empty, they are the same as what we need to show. Okay, but what does this mean? Okay, so AH is equal to BH means the following, that every element of AH can be, so if A times H1, okay, so what does this mean? So this means, okay, so this is equal to saying two things. I just want to write the equality of the two subsets to saying that AH is a subset of BH and BH is a subset of AH. That's what equality of two subsets mean. Right? Each is a subset of the other. Okay. What does this first condition mean? So this is equivalent to saying, so AH means some arbitrary AH1. Okay. BH means, so for all H1 inside H, there exists some H2 inside H such that AH1 is equal to BH2. Okay. So the one that multiplies H needs to be universally quantified, because we are trying to prove that every element of AH is inside BH. And the thing that multiplies B is existentially quantified. This is what this statement is. And this statement is symmetric. For all H1 inside H, there exists H2 inside H such that BH1 is AH2. This is what we need to show. Okay. So we need to show that if the intersection is not empty, these two conditions will hold. And these two conditions are very symmetric about each other. Okay. So we will prove one, and then that will be, and the same argument will work for the other also. Okay. So in particular, what does this say? So, okay, so I hope you are convinced that these two statements is what we need to show. So now I want to draw, okay, so we need to worry about, so let me label these things as 1 and 2. So 1 and 2 is what we need to show. Assuming that AH intersect BH is not empty. Now, a consequence of 1, we can in particular apply this statement to the case where H1 is the identity of G, which is also the identity of H. So there exists H2 inside H, okay, such that A is B times H2. So I'm applying this, I'm applying the statement with H1 equals identity. Maybe I'll just mark that here. Apply with H1 is equal to the identity element of, there's only one group, there's only one identity element. H is a subgroup of G. Similarly, a consequence of this statement is that there exists H2 inside H such that B is AH2. Okay, so this again apply H1 equals E. Okay, so both 1 and 2 themselves are, they're universally quantified over H1. So we can in particular, In particular, we can see that that statement should hold. So, but what is this? What is this saying? This is saying that A is inside BH, and this is saying B is inside AH. Okay. So this is okay. So remember, we have only the two bidirectional arrows is sort of follows from definition or or immediate. The two downward arrows that I've labeled, I mean, I've added an explanation in red. These two things, they're only one direction. They're not bidirectional. They're only one implication that we have, that is obvious, and we have used it. Okay? But now let us think about the other direction. Okay? Suppose that there exists H2 inside H such that A equals BH2. Okay. Then let H1 inside H be arbitrary. In other words, we're just saying universally quantified H1. Okay. Arbitrary. Then A H1 is B H2 H1, and this is inside BH. Okay, because H2 is inside H, H1 is inside H, the product is inside H. Okay. So what we just proved is that this apparently weaker condition also holds, I mean, is equivalent to the thing that I've circled in green. Okay. So this implication is what we just proved here. The explanation for this vertical arrow is this. So, okay, so let us just quickly recap what we are doing. We want to show that if AH1 is not empty, then we need to, I mean, we need to show that AH is equal to BH. Okay, we are now trying to analyze, trying to rewrite the condition AH equals BH in some way, in which we can prove things. Okay, so AH equals BH can be broken into two statements. AH is inside BH and BH is inside AH. Okay. It is easy to write that this condition from definition is equivalent to the two things, one and capital Roman 1 and Roman 2 that I've marked that I've circled in green. These two statements. We immediately observe that the things that are marked in that are circled in green immediately imply the statements below them, respectively below them. That is just saying A is inside BH and B is inside AH. But now we step back and think. This apparently weaker looking statement is equivalent to the green circled statements, because suppose there exists an H2 such that A equals BH2. Then if you take an arbitrary H1 inside H, then AH1 is BH2 H1, which is inside BH. So this also implies, okay. So similarly,
So A in BH happens if and only if B is in AH.
There's what? Could you repeat what you said? I didn't fully follow.
So A is in BH if and only if B is in AH.
Yeah.
So the two statements in the bottom are equivalent. That's what I'm saying.
Yeah. We'll come to that point. Yeah. I will come to that point. Yes. Yeah. So it is true. I mean, what you said is correct. A is inside BH is equivalent to A is in BH if and only if B is in AH, but yeah. Okay. So similarly, this thing here, okay, this apparently weaker looking statement on the right side is equivalent to the statement 2 circled in green. Okay. Similarly, B is inside AH. Implies that, I mean, maybe, sorry, if I write it, it's going to be wrong. Sorry, what did I speak? Sorry, I don't know where I'm missing. Okay, maybe it's here. Okay. Similarly, we get this implication. This one. Okay. So what we therefore conclude, okay, is, I mean, we need to conclude is that if AH is AH intersect BH is not empty, then these two conditions hold. A is in BH and B is in AH. Okay. So now, yes.
Why did we have to show the backward direction?
Is what? No, we need to show. We need to show. We have only okay, maybe I should clarify. We have only rewritten this condition.
Yes, so
AH is equal to,
requirement is that if the intersection is null, then this particular condition holds.
Correct. That we
like
have not
in this
proved.
Equivalence, why do we need to show the backward direction? Like that, I mean, if AH is equal to BH, then A is in BH and B is in H.
Correct.
So why did we show that if A is in BH and B is in H, then H is equal to BH? No,
sorry, I did not get your question. No, I agree. We don't need to show. Okay, but it will just simplify. Let me sorry, just for everyone. What we have shown now is that the condition AH is equal to BH is equivalent to these two statements. A is in BH and B is in AH. Equivalent. Okay, that's what we have shown. Okay. We have not shown what we set out to prove, which is that if AH is intersect BH is empty, then AH is equal to BH. Okay. So now let us finish that proof. I mean, let us. Okay. So what we have just done is rewriting the conclusion that we need to get. Okay. So now we will use the assumption and get to that new rewritten conclusion. Okay. So now assume that AH intersect BH is not empty. Okay, so let C be inside AH intersect BH. This implies that there exists an H1 and H1 and H2. There exist H1 and H2 inside H, such that C is AH1 and C is BH2. Okay. But what does this mean? This means that A, which is CH1 inverse, okay, CH1 inverse, and C is BH2 H1 inverse is inside BH, and B is CH2 inverse is what did I write? C, right? Yeah. H1 H2 inverse, and this is inside H. Okay. So this is what we showed, and this finishes. We just showed that this assumption that AH is AH intersect BH is not empty implies that A is inside BH and B is inside AH. And then we argued earlier That once we show that, we can get the desired conclusion. So maybe whatever was discussed now, let me just add as a remark. Okay. A is inside BH. Yeah, so I mean, it might look as if these there are two independent conditions that we verified, okay, but it is not. It's really one condition. So let us just make that remark. This is equivalent to saying that there exists an H inside H such that A, maybe I'll call it H1 just for the sake of BH1, which is equivalent to saying that there exists an H2 inside H such that H2 is B. H2 is, I mean, if you want to go from the second line to the third line, take H2 to be the inverse of H1. If you want to go from the third line to the second line, take H1 to be the inverse of H2. And this is equivalent to the line saying that B is inside BH. Okay. So it might, here, it might appear that we checked two conditions, but really one is, if you check one, the other one will follow. Okay. But then one still has to make this argument that it proves, you have to say something to show that this AH is inside BH. That argument will also imply that BH is inside AH. This is just a okay. So this is about cosets left. I mean something about cosets. We need to we now use this proposition. Let phi from G to H be a group homomorphism. And let K be the kernel of phi. Let A and B be elements of. So now we want to ask the following are equivalent. One. Phi of A equals phi of B. When do the two elements A and B go to the same element in H? 2. A inverse B is in the kernel. 3. B is inside AK. Okay. And 4. AK equals BK. Okay. So this is why, I mean, this is one reason why we look at cosets, okay. At least cosets of kernels. Proof. I mean, we proved essentially all of it. In the first half, the first two statements essentially in the previous lecture before the exam, and 3 and 4 now. Okay, but let's. Okay. So 1 implies 2. So phi of A inverse B is phi of A inverse times phi of B, which is phi of A inverse times phi of B, which is identity by 1. This is by 1. Okay. And this implies that A inverse B is in the kernel. That's right. Now, 2 implies, sorry, I may not be writing this proof the most optimal way, but I still want to spend time on this topic. I mean, in general, at the beginning of group theory, I would like to go a little slow. Okay. The second condition is, so A inverse B is inside K, and 2 implies 3. B can be written as A times A inverse B, and that is inside A times K. That proves 3. And 3 if and only if 4 is the previous proposition, or whatever we call it, lemma or proposition. I mean, it follows from the previous proposition. Because B is inside AK, which means their intersection is non-empty, and therefore they're equal. Okay. Follows from the previous lemma. Okay, and the remarks, etc. The discussion in the proof of the previous lemma says that this is okay. So 3 if and only 4 is what we just established today. Rest of it is okay. Except for notation, they are all things that we have done. Okay, so now we need to do yeah, 3. Sorry, I should have done 3. 3 implies 2. Okay. So what we know is that B is inside AK. So write B as A times H with H inside K. Then H is what? H is A inverse B. This is inside K. Okay, that implies 3 implies 2. Okay. And then 2 implies 1. Phi of A inverse B is E of H. But what is this? This is phi of A inverse phi of B. We are just reversing the argument of the proof of 1 implies 2. This is phi of A inverse times phi of B. So here are two elements of H whose phi of A inverse times phi of B is identity. And this implies that phi of A equals phi of B. And this is finished. Okay. So that is so that's just a property about kernel and cosets of the kernel, etc. Any questions on this? So now we would like to look at another important construction or notion related to groups. Okay. Definition. Let G and H be in elements of G. I mean, so if I write capital G, I just mean a group. Okay, I won't necessarily say it all the time. Okay. The group, elements of a group G. Okay. The conjugate of H by G is the element G H G inverse. Okay. So this is conjugate. Okay. So this is what's called a conjugate of an element. Okay. Definition. Let H be a subgroup of G. Say that H is a normal subgroup if subgroup of G if for all H inside H and for all G inside G, the conjugate GHG inverse is inside H. Okay, that is, in other words, H is close to undertaking conjugates by elements of G. Okay, so H is closed under taking conjugates of conjugates by elements of G. Okay. This is okay. So here comes. So why did we look at this now? Proposition. Okay. The kernel of a group homomorphism is a normal subgroup. Maybe I should just write it. Let phi from G to H be a normal subgroup. I'm sorry, what am I saying? Sorry, the group homomorphism. Then kernel of phi is a normal subgroup. Okay, so whenever we say normal subgroup, we have to say what is the larger group that we are discussing this. Okay, so proof. And we will see that kernels of kernels of homomorphisms are exactly the normal subgroups. Okay. What we are showing is that kernels are normal subgroups. Then we will also, later we will see that given a normal subgroup, we can always construct a homomorphism with that as the kernel. Okay, so the normal subgroups are exactly the. So the notion of normal subgroups is closely related to that of homomorphism. Okay, so this is, but right now we will see only this statement. So proof. Let H be inside the kernel of phi and G be inside G. We need to show that G inverse is inside kernel of phi. So let us apply phi to this. Note that phi of GH G inverse is phi of G, phi of H, phi of G inverse. Okay. Maybe H was not the best letter. Maybe let's call this thing. If I use the letters H, it might appear that I'm discussing an element of capital H. I don't want to. It might give the impression. Okay? But this is phi of G. Phi of A is 1. The identity element of H. Phi of G times phi of G inverse. Because this is identity, can remove, therefore, G inverse is inside kernel of phi. This is the okay. So this is one reason why why we define normal subgroups. Kernels are normal subgroups. It has, you don't need to worry about the name, but the property is this, that it is closed under taking conjugates. Okay. So now let us give some 2 examples. But before we give a non-example, we need to do something so that will be for the rest of the thing. So we know examples of some kernels. Okay. The examples. Okay. Of course, the whole group G is a normal subgroup of G. That is sort of the definition itself. To the thing containing just the identity element is a normal subgroup. Okay. Of course, if we need to find non-trivial examples, we will need, so one place where we could look is non-trivial group homomorphisms and ask for their kernel, look for their kernel. So here are two examples. Okay. So here is one which looks from the kernel, that point of view. SLNR. Okay, so this is the set of invertible n by n, not invertible. I mean invertible, but let me be more precise. N by n real matrices of determinant 1. Okay, is a normal subgroup of GLNR, which is the set of invertible n by n real matrices. Okay. Since SLNR is the kernel of the determinant map, where determinant map from GLNR to R is the group homomorphism, this which saw last time, which sends a matrix A to determinant of. So this is the kernel. So this, sorry, you can read it. So SLNR is the kernel of the determinant map. Determinant map is the map which takes a matrix to its determinant. It is a group homomorphism. If you take a product of two matrices, their determinant is also a product. And the kernel is exactly, determinant of R to R, this group. Okay. When we write GLNR, it is understood that we are discussing matrix multiplication. Here we are talking not R, but R times, meaning the non-zero elements of R with a dot, with multiplication as the matrix operation, as the group operation. Okay. So here, when we write, as the binary operation of the group. Okay. Here, when we write, okay, so here we're just taking determinants, and if you take product of two matrices, their determinant is also a product. And for another example, suppose that G is abelian. Then every subgroup of G is normal in G. Okay. Why is that so? Okay. So let H be a subgroup of G. Let H be inside H, G be inside G. Then G inverse is G inverse H. This is where the group is abelian is used. And G inverse is identical. This is inside H. So this is so here are some examples of normal subgroups. Okay. So now we would like to see okay, so one more topic, and then we would like to discuss a little bit about permutation groups. So permutation groups is an important class of groups, and they'll keep coming in many discussions. But so let us start thinking about it now, at least basics, sort of the basic structure of this. And as we go along, we will add more to our knowledge about permutation groups. Okay, so before we do, okay, so but let us just quickly finish this point. Definition. Let phi from G to H be a group homomorphism. Say that phi is an isomorphism, a group isomorphism, a group isomorphism if there exists a group homomorphism psi from H to G, such that the two composites are identity respectively, such that if you apply phi first and then psi, so this will go from G to H and back to G. This is the identity map on G, and phi psi is the identity map on H. So psi first and then phi is a map from H to G to back to H. So these two composites are the respective identity maps. So if this happens, we will say that phi is a group isomorphism. Okay. So let us make, so this looks slightly technical looking definition. How do we go and check? I mean, suppose we are given what phi looks phi. I mean, given that we are given how exactly to calculate phi. Okay? How will we determine if phi is a group isomorphism or not? I mean, how will we go and search for a psi? Okay? So it is not all that difficult. So let us make a proposition here. Let phi from G to H be a group homomorphism. Then phi is an isomorphism, is a group isomorphism if and only if phi is bijective. In other words, group isomorphisms are exactly the bijective group homomorphisms. Okay, so one could have defined it that way also, but this one tells us that there is something about the group group. I mean, there is a morphism from G to H. There's a morphism H to G, and the composites are nicely behaved. Yes, that's the proof. Okay. So suppose that phi is a group isomorphism. Then there exists psi from H to G such that psi phi is the identity map on G and phi psi is the identity map on H. But just think of these as functions. I mean, these are functions. It's just that the functions respect the group binary operations. So this implies, therefore, the first condition says that phi is injective, and the second condition says that surjective. That is, composite is injective means the first function is injective. Composite is surjective means that the second function is surjective. So this proves that it is a group of isomorphism is a bijective function. Okay? So the words injective, surjective, and bijective refer to functions from one set to another set. Okay? When we put additional structures, we will refer to them as some linear transformation or a group homomorphism or a group isomorphism. Conversely, suppose that phi is a bijective. Suppose that phi is bijective. Okay? So it has an inverse as a function. So let psi be the inverse function okay, it is inverse function from h to g. Okay, so therefore, that is psi from h to g is such that if you apply phi first and then psi, this is the identity map on G, and if you do the other way around, this is the identity map on H. So this is just as functions. Okay? What we need to show, or if we can show that psi is also a group homomorphism, then we are done. This other okay? So it's enough to show that psi is a group homomorphism. Okay. So okay, let me just what we have assumed. I mean, we have assumed that psi is a bijective. Phi is a bijective function, bijective group homomorphism. We want to show that there exists a group homomorphism from H to G. I mean, group homomorphism psi from H to G, satisfying these two conditions. We don't know yet whether there is such a group homomorphism. What we know is that because phi is bijective, there is a function satisfying these two properties. Okay? It's enough to show that function is a group homomorphism. Okay, so that's what we are doing now. So in other words, so that is psi of H1, H2 is psi of H1 times psi of H2 for all H1, H2 inside H. Okay, so this is what we need to show. Okay. Sorry, just recheck what I wrote. Yeah. Okay. So let us write psi of H1, H2 as G. So we would like to show that maybe I'm going in a roundabout way. So then phi of G is H1, H2. This is phi of sorry, I'm sorry, my notes. I seem to have written something which I cannot make out from my notes. Just give me 1 minute. Psi of H1, H2, what I need to show. So H1, H2, we maybe just give me 1 minute. Sorry, just give me 1 minute. Sorry, I wrote some stuff which not doesn't make any sense now. H1, H2, H1 is phi of this H2.
Sir,
Yeah.
sir, phi of
No,
phi.
wait. Let me just. Yeah, I wrote something in my notes. Let me just quickly fix it, and then I'll write here. Just give me a minute.
Okay, sir.
Yeah, correct. Okay, so I'll fix it. Just a minute. I wrote something which didn't make sense. Okay, this. Okay, so let us write. So let G1 and G2 inside G be such that HI is phi of GI, I1 and 2. So then let us write this whole thing. Psi of H1, H2 is psi of phi G1, phi G2. That is just individually replacing the HI with the corresponding phi GI. But phi is a group homomorphism, so we can put the things inside. And psi is the inverse function of phi, so this is G1, G2. So this is one thing. And okay, psi of HI is psi of phi of GI. This is GI for I equals 1n. Okay. That's exactly what we needed to show. So this shows in this box. Yeah, I tried to, I manipulated it some other way and had a mistake. Okay. So yeah, so this, I mean, the summary is this. If you're given a group homomorphism, and if you can independently check that it is bijective, then it is automatic that the inverse function is a group homomorphism. And that will prove that the okay, so maybe let me add that as a remark here. Remark. Okay. What we just showed is that if phi from G to H is a bijective group homomorphism, then phi inverse as a function is a group homomorphism. Therefore, both phi and phi inverse are group isomorphisms. So, I mean, the notion of a group isomorphism, if two groups are isomorphic, they behave in exactly the same way. This is what that's. Sorry. Okay. Sorry, I spent. Okay. So another remark that we can make. Let phi from G to H be an injective group homomorphism. Okay. Then phi gives an isomorphism from G to image of phi. So in other words, you can think of G as I mean, G is isomorphic to a subgroup of H. Okay? And for all group theoretic purposes, we can think of G itself as a subgroup of H. Okay? So this makes G isomorphic to a subgroup of H. So this is a okay. This is just some general remarks about isomorphism. So we'll come back to these things as we proceed. It is not, as we learn more things, as we see more examples, we will revisit these topics. What is an isomorphism? That sort of things. Okay. So okay. So the next thing I want to discuss is permutation. So why are they? I mean, as you study more algebra, you will see that permutation groups come up in many contexts. So it is, and it's also some concrete class of groups in which we can write down elements, we can work with, etc. Okay, so this is and that's not the only reason why we want to look at permutation groups as a good class of examples. Okay. As I said, as you proceed to study more algebra, you'll see permutation groups, their subgroups, etc., coming up. So we want to start with an an observation, which sort of also justifies why it is important to study permutation groups. So definition. Let G be an element of H. Sorry, I should not call this. Let me just call this a discussion. So I want to also not make assertions along the way. Okay. The function phi G from G to G. It is a function, not a group homomorphism. It takes an element H to G times H. Is bijective. Okay. This is not a group homomorphism. It takes identity element of G to G. I mean, E to G. So this is not a group homomorphism. Okay, so this is important. Maybe I mean, okay, unless E in general, unless G equals identity. So in general, it's not a group homomorphism. But it is still, I mean, let us still look at this function. It is bijective. Okay. Now, consider capital phi from G to the set of bijective functions. Sorry, let me just make sure I am using consistent notation. Just give me 1 minute. I just need to pull up last week's notes, last lecture's notes. Sorry, just a minute. There was no, yeah. Okay. So this notation by bij of x was the set of bijective functions from x to itself. So we can talk about bijective functions from g to g, in which little g goes to phi g. Okay. So let us now consider the function. So I'm thinking about the function phi sub little g, which takes an element h to g times h. Okay. This is a bijective function from g to g. So little phi g is an element of this bijective x, bijective g. Okay. And so for every, so now consider this function. Okay, so I will make an assertion here because I want to sort of conclude this. I will prove the assertion next time. Phi is a group homomorphism. So we have already observed that this is if you given any set, the set of bijective functions from that set to itself is a group homomorphism under group under composition. So this is a group under composition. Okay. And this is a group with a given structure. Okay. So this requires not a complicated check, but can be confusing. So I will do it in the next lecture. Okay. So this is proof in the next lecture. But for now, I mean, just because I'm running out of time, because I want to. Okay. But we also observe if you had a finite set, what is the set of bijective functions? Okay. So suppose now that G has n elements. G is a finite group. Okay. It's n element of cardinality n, of size n, of order n. Okay. So that is cardinality of the set G is n. Okay. Then the set of bijective functions on G is isomorphic to Sn. Okay. Why is that? G is a set of with n elements. A bijective function just means, so we can actually call those elements 1 through n. And a bijective function just means 1 goes somewhere, 2 goes somewhere, 3 goes somewhere, and it is injective. I mean, it is injective and surjective. So in other words, it is just a permutation of 1 through n. Okay. So bijective functions on G is isomorphic to Sn. So in other words, therefore, we have so therefore G is isomorphic to a subgroup of S. Because we observed earlier that if you have an that we have said that okay, phi is injective. Okay. Again, proof in the next lecture. Okay. So this function phi, in which a group element gives the bijective function given by multiplication by that group element. Okay. So okay, I mean, this may be the sort of maybe the first time you are seeing these sort of meta definition. It's not a meta definition. It's not, I mean, you start defining a function, then you get a collection of functions. Now you want to think of a function like this. Okay, so please spend time reading this discussion. And if you have any questions, please do ask me in the next lecture itself. So this sort of things we will keep doing. Okay. So if you lose track now, it may be difficult. I mean, I should not say, I'm not saying it's impossible, but things will just pile up. Okay, that's that. For that reason, please make sure that it is clear what we're doing here. This, I mean, this may be the first time you start seeing things done like this, I mean, these sort of definitions. Subgroup of Sn. Okay, this is so. Okay, so this is called Cayley's theorem. So we'll revisit this point next time because I need to prove the key points again. I mean, I have not yet proved the key points. This is called Cayley's. Okay, so we'll prove this. I mean, we'll prove. We will revisit this discussion in the next lecture. And so in other words, every finite subgroup, I mean, every finite group is isomorphic to a subgroup of Sn for some appropriate n. So this also tells us that somehow, of course, Sns themselves are finite subgroups, finite groups. But so this somehow tells us that I mean, the class of permutation groups Sn, I mean, as n runs over all integers, positive integers, this is it is an important object. I mean, something that one should try to understand. Okay, so for that, so the next lecture is, I mean, next lecture a little bit sort of aimed at understanding permutation groups, okay, which we will do beginning. So we'll fill in these gaps in the next lecture. Then we will look at basics about permutation groups. So after that, we'll discuss this notion of a group acting on sets. Then we will prove various things that could be understood in, using that vocabulary. Again, yeah. Okay? So it's that's the plan for the next. So whatever I wanted to say about permutation groups, it is too short now to say it. So I postpone all of it to the next lecture. So I'll stop here. Any questions?